Hello. This lecture is part 2 of Section 1.3 from Math 311, a linear algebra class at Western Illinois University. This topic is still lines and planes, and today we're going to be talking about planes, particularly planes in the usual sense, in 3 dimensions. Now, we're going to see that the planes are just, in a way, they're generalizations of lines, even though they're quite different. Lines are one-dimensional. Planes, we're going to see, are two-dimensional. But they can be defined in the same way. If you recall, we could define, there were many ways to define a line in R2. And one of them was with a normal vector. That is, if we specified not necessarily a direction vector, but a normal vector perpendicular to our line, such that the vector connecting any 2 points on our line was orthogonal to n. That is, if we have this point x, an arbitrary point xy, and then a fixed point x0, y0 on the line, we've got this vector x minus p, where, of course, x, in this case, the vector x was xy, okay, and p was the point x0, y0, right? Then we define it this way, and that's a dot product, okay, because we wanted these vectors to be orthogonal, and when we multiplied things out, we got something times x plus something times y equals some constant, which is the general form of an equation of a line in R2. Well, we can do the same thing in 3 dimensions. If we take n to be a 3-dimensional vector and take a point in 3 space, then we can, once again, in this case, we can let x, if we let x, once again, be x, y, z, and p be x0, y0, z0, and n be a, b, c in this case. And we can still write down this equation. It makes sense. And then if we take the dot product, we get a times x minus x0 plus b times y minus y0 plus c times z minus z0 equals 0. And we can distribute things and take these constant terms to the other side. And now we get ax plus by plus cz equals d. So when you have a constant times x plus a constant times y plus a constant times z equals d, this equation is called the general form of the plane, of this particular plane in R3. Okay, and we're going to see exactly that this is a 2-dimensional thing. Right now, all we know is that this generates solutions of this equation. So let's look at a specific example. Say if we wanted to find the plane with the normal, and I should say that n, just as in the other case, n is what we call the normal vector. The normal vector of our plane here. So if we want to find the plane with normal vector 2, 1, negative 5, containing the point 1, 1, 2, all right, so this is our x0, y0, z0, and this is ABC, this is n. So n is 2, 1, negative 5, and p, take p to the vector 1, 1, 2, and x again is x, y, z. So what we get is 2, we start with the dot product, okay, this is going to be 2, well, I'll write this out, 2, 1, negative 5, dot product, dot x minus 1, y minus 1, z minus 2. And then this becomes, so with the dot product, then we want this to be 0. So we get 2 times x minus 1 plus 1 times y minus 1 minus 5 times z minus 2 equals 0. And you can multiply things out again. This will be 2x minus 2 plus y minus 1. I'm sorry, this will be 2x minus 2, y minus 1 minus 5z plus 10. So you'll have 2x plus y minus 5z plus 7 equals 0, and you could subtract 7 from both sides, and you get minus 7. Okay, so here's our general form. Okay, so that's the general form of the equation of this plane, which we're going to show that this is indeed two-dimensional. So how do we do that? It's not as hard as you would think, because back in R, if you look back in R2, we could write y in terms of x, right? And then we could write the vector xy as, just some constant vector plus x times another vector, if you remember that from the last video. Well, we can do the same thing here. As we can, in this case, we can do this with really any variable we want. Because these coefficients are all non-zero, we could write one variable in terms of the other two. But it's going to be particularly easy because we just have a y by itself here. So we can see that y will be equal to negative 7 minus 2x plus 5z. And so we got to a typical point is on the plane. We denote it by this vector, x, y, z. This is going to be x minus 7 minus 2x plus 5z, z. And then we can write this in terms of x and z. Well, first we can write this as 0, negative 7, 0. And then we can write this as x times what? Well, it would be, this is x times 1, minus 2, 0, plus z, 0, 5, and 1. Okay. Now, we can see that this, and we're not really putting any restrictions on x and z, right? Because this equation right here is basically equivalent to this equation, right? So as long as y satisfies this equation, that's all we need. And x and z can be basically anything we want. So that means any linear combination of these two vectors plus the vector 0, negative 7, 0 will give us a point in the plane. And because it doesn't really matter really what these real numbers we call, we could replace x with r and z with s, and that would still work. We can just let s and r be any real numbers we want. Now, just one other thing though, you should keep in mind that these two vectors right here, these are not going to do not correspond to points in the plane, but they are orthogonal to the vector for the normal vector 2, 1, negative 5, right? Because if you take the dot product, 2 times 1 plus 1 times negative 2 plus 0, that's 0. And 0 plus 5 times 1 plus 1 times negative 5, that's 0. Okay, so you have two vectors here. They're not parallel, they're not multiples of each other, but they are both orthogonal to our normal vector. Now, and that's the way how all these planes in R3 work. So we can give you the official definition now. Given a normal vector and a point, we can define a plane containing that point with normal vector n to be the set of all points x, y, z, such that n dot the quantity x minus p equals 0, where x and p are defined as what they were before. And as before, we could multiply this out, and we'll get something times x plus something times y plus something times z equals a constant d. That's the general form. And then just like we did before, because we're going to have two degrees of freedom, right? We came up with two vectors that were orthogonal to the normal vector, u and v, and so any point in the plane corresponds to a linear combination of this vectors in this form. Okay, if you just look at this, this was our p, this was our u, and this was our v. Okay. All right. Now, it turns out that, and back to this form, and of course this is the vector form, what we call the vector form of the equation of a plane. And so in your homework, they'll ask for a general form and a vector form. That's what this is. Now, it turns out that as long as u and v are not parallel, that is, if they're not scalar multiples of each other, we can pick u and v to be anything, as long as they're not parallel, and p to be anything, and the set of vectors of this form will be a plane. Okay. By the way, as we should see now, even though we haven't defined dimension officially, we can see there it's two-dimensional because there's 2 degrees of freedom, one choice for R, one choice for S. Okay. Another way of thinking about that is any ordered pair RS will correspond to a point on the plane. All right. So this always gives us a plane. The set of vectors like this will always give us a plane. And as long to find the normal vector, let's say if we just want to start with this and say, okay, what's the equation of the plane by finding a normal vector? We just need, in this case, the normal vector n needs to be orthogonal to u and v. Okay. And then once we know the normal vector, then finding the equation of the plane is easy. Now, I just want to say this leads us to a very important geometrical idea, which you've probably seen, hopefully you've heard before, is that 3 points in space determine a plane, as long as they're not collinear. Okay, 3 non-collinear points determine a unique plane. Just made 3 points in R3. Okay, and the reason for that is we can create a vector from the first point and the second point, and another for the first point and the third point. These are certainly not going to be, as long as the points are not collinear, these vectors are not multiples of each other. And as long as we can let this be u and we can let this be v, and then as long as we can find a normal vector that's orthogonal to both of these, then we're in business. Now, those of you who have had calculus before, multivariate calculus, know that you can do this. You can do this with determinants and doing this. There's a way there. There's a special way you can define the vector orthogonal to these two vectors, and I'm drawing a blank right now, but I think those of you who have calculus, you know what I'm talking about. We're going to go through a different way of finding this. So in our next example 2, let's just do with this example. So let's find the plane passing through the points P, Q, and R. So we want to first find PQ, and we know how to do that. 3 minus 1 is 2. Negative 1 minus 2 is negative 3. And 1 minus 0 is 1. And then PR is negative 2 minus 1. That's negative 3. 4 minus 2 is 2. And 3 minus 0 is 3. Okay. All right. And then we'll let n be just A, B, and C. And we want to find numbers A, B, and C for which this works. Okay, so PQ dot N is going to be 2A minus 3B plus C. And we want this to be 0. And then PR dot N is going to be negative 3A plus 2B plus 3C. And we also want that to be 0. Now, this is a system of two equations and 3 unknowns. We're going to talk a lot more about systems of equations in the next chapter. But it turned out in general, when you have more variables in equations, you're going to get not just one solution, but many solutions. As long as, the things are nice, and by saying that the equations are not multiples or linear combinations of each other. So we're going to have a whole chapter of finding out how to solve equations like this with some methods. But right now, I'm just going to do a little substitution trick. I know the C is all alone here, so this tells us that C is going to be minus 2A plus 3B. Okay, and then I'm going to plug that into this equation down here, and we'll get minus 3A plus 2B plus 3 times minus 2A plus 3B equals 0. And then if we collect like terms, we get minus 3A minus 6A, that's minus 9A. And 2B plus 9B is 11B. That's 0. And now we can write A in terms of B or B in terms of A, whichever you want. 11B will be 9A. And so B is going to be 9/11ths A. Right? So this kind of indicates that we'll get a solution. We can let A be anything, and that will give us a solution as long as this whole B is defined this way and C is defined this way. All right. So I'm going to pick a value of A that is nice, and by nice I mean so we can avoid fractions. If you want to pick A equals 1, that's fine. Obviously, you don't want A to be 0, because that gives then everything else 0. We want a non-trivial solution to this. I'm going to pick A equals 11, just so we don't have to deal with fractions. So we let A equals 11. B then is going to be 9/11ths times 11, that's 9. And then C, remember, is going to be negative 2 times 11 plus 3B, which is, we know it's 9. It's going to be minus 22 plus 27, or 5. Okay. So we can let N be the vector 11, 9, 5. Now we can check that this is orthogonal to both of these vectors, because the dot product will be 22 minus 27 plus 5, that's 0. And if we take the dot product of this, we'll have negative 33 plus 18 plus 15, and that should be 0 as well. Okay. All right. So now what's our equation is going to be 11 times now, and we're going to pick a point here. It really doesn't matter which one we choose. I'm going to pick Q because just to make it a little more interesting rather than all these than the 0 here. I'm just going to pick this point 3, negative 1, 1. All right. So then this will be 11 times x minus 3 plus 9 times y plus 1 plus 5 times z minus 1. That comes from here. And that's 0. Okay, multiplying things out, this will be 11x minus 33 plus 9y plus 9 plus 5z minus 5 equals 0. And this is going to be, see if I did this, if we did this right, it should be 11x plus 9y plus 5z equals 29. And we can check, we can just by plugging these other points in, if we 1, 2, this will be 11 times 1 plus 9 times 2, that's going to be 11 plus 18, that's 29, right? And you can check that this will work out for the other 2 points, I think. So that's the general form. And then if we want the vector form, we can pick a variable. It doesn't matter because all the coefficients are negative or non-zero. So we can write, pick z again. So I'll get this 5z will be 29 minus 11x minus 9y. And so this will be, so z, we can divide both sides by 5. So x, y, z can be written as, well, x times, well, let's just do all the steps here. So x, y, z is going to be x, y times this expression. Okay. And then we can write this as x times 1, 0, negative 11 fifths plus y times 0, 1, negative 9 fifths plus the constant vector 0, 0, 29 fifths. Okay. All right. And we could, again, x and y really can be anything we want. So visually we could replace the x with r and this with s. Okay. It's a little easier, just, you know, can use, look at it that way. So that would be the vector equation of this plane. I should say that you can check that both of these vectors will be orthogonal to the normal vector. For example, if you 11 times this plus 9 times this times 5 times this will be 0. Okay, and any scalar multiple of this vector will also be orthogonal to n, and any scalar multiple of this will be orthogonal to n. So if you want, you could actually replace this with any. We can multiply this vector by 5, and it will still work. So it'll be 5, 0, negative 11. And if we multiply this by 5, we get 0, 5, negative 9. Okay, and now this we should keep here as it is, because this is a constant vector. Okay, so here's r, here's s. Okay, so a point in this plane corresponds to any linear combination of vectors of this form. Okay, some tidbits before we wrap up. Context is important. Okay, in R2, x plus y gives us a line because it's an R2. In R3, x plus y equals 1 is actually a plane because this is actually, the z is not seen there, but it's still there. It's 1x plus 1y plus 0z equals 1. So this has normal vector, 1, 1, 0. Okay, so this is a plane, and in fact, what will be going on here, say in 3 space, if this is the x and y plane, the line x plus y equals 1 or maybe this is x minus y equals 1, but let's say this is x minus y equals 1, or minus x equals 1, okay, something like that. This correspond to this line, but then we'd also include all the stuff that's above and below that, okay? So it's in 3 dimensions. Okay, because when you have something like this, when there's no mention of z can be anything it wants, okay? Points still have a z coordinate. It can just be anything we want it to be. Then the last thing here is we can do this in any dimension we want. You know, this equation n dot x minus p equals 0. This makes sense in any dimension as long as n, x, and p have the same length, right? So that defines a new object in Rn, which we may or may not be able to understand. Like in this case, we have, if we let our variables be x, y, z, and w to represent the 4 coordinates in R4, and this equation will give us an object called a hyperplane. A hyperplane is a generalization of a regular plane. And just to so even though we can't view things in 4 dimensions very well, we can still get we can do the same thing we did before in getting this to looking what an arbitrary point looks like, because we can write one variable in terms of the others. In particular, x will be 5 minus 2y minus 3z minus 4w, right? And so the coordinate, the vector x, y, z, w can be written as 5 minus 2y minus 3z minus 4w, y, z, w. And this can be written as 5, 0, 0, 0 plus y times negative 2, 1, 0, 0 plus z times negative 3, 0, 1, 0 plus w times negative 4, 0, 0, 1. Okay. And where we can let y, z, and w can be any real numbers we want. So now we actually have a 3-dimensional object in 4 space. And in general, a hyperplane, like a hyperplane in n dimensions, is going to be n minus 1 dimensions. You're going to have 1 dimension less, and it's all just hyperplane. Hyperplane in Rn is given by an equation where you have some number times the first variable plus some number times the second variable plus dot 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 some number times the nth variable equals a constant, and that's a hyperplane. Okay, which is not exactly what we're going to talk about in this, but I thought it's something I should share with you. Okay, that's all. Now, in our next video, we're going to actually see some geometric applications of lines and planes.